Do you remember these things? It was the hottest thing from April 2017 to July 2017, fidget spinners. So I don't know if you could see it through the camera, but if you hold it in person, there's a particular floral curvy pattern that you can see that appears on the as you rotate it. So this fidget spinner has 4 gears. There's a central one and 3 other gears that goes around it. There's 12 teeth coming out of it. And if I hold the bottom and rotate it, all the gears are going to turn around the central gear. And if you trace out this gear teeth, it traces out a certain curve throughout the space, and that's what you can see here. Let's work out the equation of that thing. But before that, let's talk about what we're going to talk about. I want to talk about parametric equations. So we talked about parametric equations for lines. Now I want to start to talk about like curvy curves. Doesn't have to be quadratic, any kind of function. Okay, let's jump to the notes. Okay, so I'm actually touching on more than 2 chapters here. We're right about to start chapter 12 on vector functions. Vector functions, chapter 12. But actually, it touches a little bit on chapter 10 too. And chapter 10 is about parametric equations. And those are 2 different perspectives on pretty much the same mathematical object. So I'm going to talk a little bit about both, but mainly we're going to follow chapter 12. So what do I mean by mainly the same thing? Well, parametric equations look like this. So you could imagine a 3-dimensional point for every different t that you plug in. So you have changing x coordinate function f of t, and then you have different function for different coordinates y and z. So every t you plug in is a different 3-dimensional point in space, and then you can kind of imagine this point moving through space, like a particle moving through space. Vector function is pretty much the same thing. You have x component, y component, z component, and the object you're looking at is a vector, not a point. But pretty much the same thing, right? I mean, we're just switching the parentheses on the left and right, swapping that out for angled brackets. Yeah, they're different mathematical objects, but like pretty much the same mathematics applies. So we're going to look at both of these a little bit interchangeably and talk about both at the same time. Okay, so let's look at a couple of examples. So one example you've already seen is kind of parametric or vector version of line, right? So x equals to 5 plus t, y equals to 1 plus 4t, and z equals to 3 minus 2t. So this is the form. So f of t is the 5 plus t, and g of t is the 1 plus 4t, and h is the formula for z there. I don't have to restrict the domain, but let's just say t is only between 0 and 1. So if t is equal to 0 and I plug in 0, I get the point 513 here. And if I plug in t equals to 1, I get 5 plus 1 is 6, 1 plus 4 is 5, and 3 minus 2 is 1. So I get the point 651. And the point changes kind of in a direct straight line from 513 to 651. Excuse me. So this is a line segment in 3D. So it's like a segment of a line that we've been working with. So this is an example parametric equation or vector function if you change the parentheses to a angled bracket. Okay. Let's look at a different one. So it doesn't have to be a linear function. Let's look at trig functions in there. So this is a little bit more difficult to look at, but we know from trig that if we look at the two-dimensional curve cosine t sine t, that traces out a unit circle in counterclockwise direction from 0 to 2 pi. So that's what that would do for two-dimensional parametric equation. But it's a little bit different here. One difference is that I have a 2 and a 3 in front of the cosine and sine. So that kind of stretches the picture a little bit, right? So if you stretch it in x direction 2 units, so now it's no longer a unit circle. It goes 2 to the right and 2 to the left. And multiplying y value by 3 will change the y values from -3 to +3. So it would trace out an ellipse like that, but it's still similar to a circle, right? So I think we can handle that, but it's only in x and y direction. So that is happening in the xy plane. Okay, so you start with the positive x-axis and kind of go counterclockwise and wrap around. But as it's doing that in the xy plane, the z value is actually increasing. So z value, so if you kind of trace out what happens in the ellipse shadow, the actual curve is slowly rising from this shadow ellipse. And we're actually going to 3 pi, not 2 pi. So it wraps around once and wraps around like halfway through the second round. So it starts at height 0 at the positive x-axis at 2. And it goes 1.5 times around, kind of directly above this blue shadow that I've drawn. I hope the picture looks reasonable. And then after 3 pi, right? This is pi, 2 pi, and then 3 pi. So it wraps around once and then go all the way back to the back end. And at that point, the height is at 3 pi. Z is equal to 3 pi. So you might call this something like oval helix. So I hope that curve made sense. All right, so these are examples of parametric equations and vector functions. Let's look at the fidget spinner curve. So this was a two-dimensional curve. So let's focus on 2 dimensions. It was made up of 4 gears of the same radius. So let's just make the radius of each gear 1 unit long. So what's happening to this fidget spinner? So I usually flick it to go clockwise direction. That's what I naturally do with my left hand. So let's make it go that way. So let's first work out what the center of this gear is doing. So it's going to wrap in clockwise direction. And because each gear has a radius 1, the center of the gear to the right is 2 units away from the origin. And the center of that gear goes in a circular motion in clockwise direction. So 2 cosine t and 2 sine t. This would trace out the center of the gear, but the floral pattern that we were seeing when I was flicking the fidget spinner was those curves were drawn by the gear themselves. So I counted them. Each gear has 12 teeth going around. And let's look at what's happening to the very rightmost gear tooth, as it went around. So the center gear also has 12 teeth. So as it goes around, the gear rotates in contact with the center gear exactly once. But as it's rotating, it's also going around the gear as well. So it actually makes 2 complete rotation as it goes around the central gear. I hope that made sense. So if like you kind of look at 2 stationary gear and just kind of rotated the gears themselves, they go around once, but it's also, the whole thing is also rotating. So that is going in a clockwise direction. And so it wraps around twice in a time that the center of the gear wraps around once. So it should be cosine of 2t and sine of 2t. I'm multiplying the inside by 2 because it goes through the entire period twice as this t goes from 0 to 2 pi. So t is changing from 0 to 2 pi. Okay, and I wrote it a little bit wrong. This is a picture where it goes counterclockwise because cosine and sine usually goes counterclockwise direction from positive x-axis. So I should really replace the t with negative t. So it goes in clockwise direction instead. Okay, but I could simplify this a little bit. Cosine is an even function, so that means that the negative sign inside doesn't do anything. So I could drop the negative sign inside of the cosine, and that doesn't matter. And for sine, it does matter, but sine is an odd function, so I can pull the negative sign outside of the function. So I don't know if it's any simpler, but I'm going to pull it out. Okay. That's what the curve looks like. Let's see if we can see that picture. I'm going to draw this in Desmos. Okay, so here's Desmos. Okay, so I had cosine of t plus, oh wait, it was 2 times cosine of t plus cosine of 2t. That was the x component. And it was negative 2 times sine of t minus sine 2t. Okay, I'm starting to see things here. And you went from 0 to 2 pi. Okay, and this is what the each gear tooth, each gear teeth is tracing out the space. Now, I know what you're thinking. This doesn't look like the floral pattern that we saw, but remember there's 12 different teeth for each gear. So actually, if I copy this, and so what's happening with the other teeth? Well, the center of the gear is tracing the same graph, but within that gear, it's starting 1/12 of a rotation ahead of the other gear. So what I would do is I'm going to add the angle 2 pi over 12 or pi over 6. Okay. And again, I'm going to go from 0 to 2 pi. Okay. So this is what the second gear on the same is tracing out. And you can kind of see that if I shifted this picture, I really don't want to do too many of these because I don't think you have the patience to sit there while I type 12 of these things out. But you can kind of see that the floral pattern is now developing. So there's a lot of crisscross happening, and then near the inside, there's some kind of these, I don't know what you call these cusps forming near the center. So there's gonna be 12 of these kind of touching, I guess, the circle of radius 1 near the center. It's going to be 12 equally spaced cusps there. So we were able to work out the curve. I'm pretty happy with that. Okay, so that's the fidget spinner curve. Okay, so we're writing down these parametric equations, and sometimes we want the equation without the parameter t in it. So you should know a couple of the techniques when you have parametric equations, how you could kind of deparameterize it. Like how do you take out that parameter t? So there's a couple techniques you should know. So one way is that when you have equations like this, you could solve for the parameter t. So from the first equation, if I solve for t, subtract 2, and then divide by 3, I have solved for t, and then kind of substitute the t into the second equation. Okay, so that's, if I distribute the negative sign, I get plus 2/3 minus 1. So, okay. So now this is in the more traditional y equals mx plus b type of form. So now I have an equation of a line without the t in it. And it doesn't have to be a line. As long as you can solve for t and substitute, you can solve for the equation that way. Another technique that's useful is to use this cosine squared plus sine squared is equal to 1. So you can use this to sometimes reduce the parametric equation into equation without the t in it. So for example, if I look at these equations, I see that one of them has cosine in it and the other one has sine in it. So solve for cosine and sine. So from the first equation, I could write it as x minus 1 is 2 cosine of t. So x minus 1 over 2 is equal to cosine of t. The second equation is a little bit simpler. I just divide by 5. Okay. And then if I take these and square and add it to each other, I should get 1, right? Cosine squared plus sine squared is equal to 1. So combine it. I get x minus 1 over 2 squared plus y over 5 squared equals to 1. And this is an equation of an ellipse. Right? Ellipse with the center 1, 0. That's the center. And it looks like it has the semi-minor axis radius of 2. And it has the semi-major radius of 5. So we trace out an ellipse like that. Okay, so you should know those two techniques. So sometimes you want to come up with a formula for that curve without t in it. So I expect you to be able to do that. Okay. All right. So let's talk about the parametric equations and vector functions themselves. So usually when we look at a function, the domain is a value that we can plug into the function itself. But the domains are different for different functions. So what do you do if the domains don't agree? For example, let's look at this equation right here. So this is a vector function. And it looks like x and y component has t and t cubed. And I can plug in any t and make sense of this. I could plug in positive, negative t, 0. Everything goes. Any real number will do. But the z component, we can't plug in a negative number into a square root function and get a real number out. So the domain for the third component, you could still plug in 0 into square root. So non-negative numbers. So from 0 off to infinity. So any real number is okay here. Any real number is okay here. But the only non-negative numbers are okay here. So what do you do when you get something like this? Well, you kind of go with the most restrictive domain. If it doesn't make sense for some part of the function or some component, then it doesn't make sense for the whole vector. So the domain is from 0 to infinity for this function. Let's do another one. So here's another vector function right here. Okay. So the inverse sine function is limited between -1 and +1, including the endpoints. Let's see. The natural log function, you can't plug in negative or 0 into natural log function. So t has to be positive. So from 0 to infinity, not including the 0. And for the z component, 1 makes sense no matter what t is, right? So t is even appearing in the formula. So any real number is okay. So again, we have disagreement in the domain. So we just choose the most restrictive domain. So we can't do from -1 to 0 because this function doesn't make sense. But we can't go greater than 1 either because this equation doesn't make sense. So the domain for vector function v is from 0 to 1, right? It has to be positive, and it could be no bigger than 1, right? So that's the domain. T is strictly greater than 0, but less than or equal to 1. I hope that made sense. So this is the only interval where both the x and y component make sense. Okay. So we take the similar approach for when we start to talk about calculus. So the first thing we're going to talk about is limits. If we're talking about a limit, we take limit component-wise. So you take the limit of the x component, y component, z component separately. And the limit only makes sense if all of them make sense. Remember, limit doesn't have to exist, right? Maybe they blow up to infinity, or maybe they oscillate, or maybe there's a jump. Sometimes the limit doesn't exist. So here, the limit of t squared goes to 0 as t approaches 0, because t squared and t cubed is a polynomial, and they're continuous, so I could just plug it in. The limit of this thing is a little bit more difficult. Maybe you remember L'Hopital's rule from Calc 1. So if you have a 0 over 0 situation, so if I had just plugged in t equals to 0, I get 0 divided by 0. But when you have something like that, we can take the derivative of top and bottom and then plug in 0. So derivative of sine is cosine, and derivative of t is 1. So here I'm using L'Hopital's rule. And then I plug in t equals to 0. So cosine of 0 is now 1, and I'm dividing by 1. So we get the limit of 1. Okay, so you can take the limit by doing the limit for each component. So the limit is the vector 0, 0, 1. It's the unit vector k. Okay, let's look at another limit. Okay, so arcsine is a continuous function at 0. So you can, arcsine of 0 is equal to 0. It's approaching 0. 1 is a constant, so that approaches 1. Natural log, though, the graph of natural log looks like this. As it approaches 0, it shoots down to negative infinity. So the limit doesn't exist here. And if the limit doesn't exist for one component, it doesn't exist for the entire vector function. So for the limit to exist, all three components has to have a limit. Otherwise, the whole limit is ruined. So the x component and the z component is stabilizing. It's getting closer and closer to something. But the y component is going to negative infinity. So the vector is just kind of shooting off into the negative infinity y direction. It gets longer and longer, and it doesn't settle down to a single vector. So we take the same approach as kind of the domain. For the limit to exist, every single component has to have a limit. So we take the very restrictive definition of a limit there. Okay, so that might come into questions about continuity. So in one dimension, we say function is continuous if it satisfies three things. First, the limit has to exist. And the function has to be defined at that point. So that's number two. And number three, the limit and the value have to agree. So it's getting closer and closer to the value that it's that you get when you plug it in. So the same thing with vector function here. When we're talking about continuity or vector function or parametric function, each of the limit for each of the component has to exist. Each of the function has to be defined. The vector, each of the components of the vector function has to be defined, and they has to agree. So all three components have to agree at the same time. All right, I think I'm gonna end the video here. Next time we'll talk about derivatives and integrals. All right, I'll see you guys later.